This module demonstrates the capabilities featured in CTD's threat detection portion. We'll start off with some general definitions. Next, we'll describe why it is securing industrial networks is a bit more challenging than securing typical IT networks. After that, we'll separate the alerts we see within CTD into their two different categories. Following this, we'll demonstrate what capabilities a cybersecurity solution must have in order to hunt threats quickly and efficiently. Finally, I'll use our demo system to show you the CTD user interface and give a quick demonstration of how the features work. Before explaining how to use CTD's threat detection capability, it will be of benefit to explain what a threat is in context of cybersecurity. The term threat refers to any event within the process control network that has a negative or unwanted effect on the overall operation of the site. Threats are typically, but not necessarily, introduced by what are termed threat actors. These are human influencers, such as hackers, that exploit network-related vulnerabilities in order to penetrate the network. However, it is important to know that threat actors are not the only factors that can threaten a system. As mentioned earlier, threats can be divided into two categories. The first is malicious behavior. This refers to any behavior that happens with intent to cause operational disruption. Malicious behavior can be further divided into two subcategories. The first is collateral damage. This typically refers to IT native attacks, which then propagate to the process control network, infecting OT devices due to the convergence of IT and OT. A good example of this is NotPetya. This was an encrypting malware infection that was able to jump from corporate IT networks to industrial OT networks, and from there begin running one of three network propagation methods: Eternal Blue, Eternal Romance, and exploitation of SMB version 1. Within seconds, the malware would propagate through Windows-based machines using the SMB networking protocol for peer-to-peer file sharing. Collateral damage actually accounts for most OT-related cybercrime incidents that have taken place in the past. The second subcategory of malicious behavior consists of targeted attacks. This term refers to attacks that specifically target critical OT infrastructure and are purpose-built to damage infrastructure or impede production capabilities. Targeted attacks against industrial systems have increased at a rapid rate over the past few years. They are typically aimed at specific market verticals, such as oil and gas manufacturing, power generation utilities, the pharmaceutical sector, and so on. A typical example was the Triton attack. Triton was created specifically to target Triconex's industrial safety systems made by Schneider Electric, with the infection first manifesting at a Saudi Arabian petrochemical plant. The second main threat category in the threat landscape, introduced by what is referred to as the human surface. This refers to all exploitable security gaps introduced by whatever humans are in the equation. Action on the human side could be deliberate or accidental. Cyber incidents could result from factors as diverse as lack of training, a disgruntled employee harboring a grudge, lack of experience, or even tiredness leading to human error. No matter what the cause, we must always keep in mind that even small mistakes could lead to catastrophes. Now, industrial security has a unique nature when compared to IT security. The differences between IT and OT security introduce challenges that make it more difficult to maintain an overall security posture, and thus ongoing production operations, in the face of the current threat landscape. To start, unlike IT environments, OT environments consist of multiple assets per device operator. As a typical example of that, I myself have one personal computer. Within my office environment, this is the only hardware device for which I am responsible. Easy! However, this is typically not the case for OT engineers. An OT engineer may be responsible for many hundreds of devices, and each one of them represents a potential vulnerability or point of attack. In the worst-case scenario, one compromised device could represent a single point of failure. To put it simply, depending on the way the system is configured, a single compromised device could potentially shut down operations across the entire site. To make the situation worse, a single operator responsible for a multitude of OT devices simply can't ensure the security of all those devices single-handedly. In many cases, the operators themselves have no idea which devices are populating their network. As we saw in the visibility module, Without visibility, you can't protect an environment from penetration. Something that is often not taken into consideration is that OT environments are typically not built with security in mind. OT environments are unique in their functionality and in their infrastructure, and the risk their distinctiveness presents to their security posture is much greater than in a typical IT network. This is particularly true within OT in terms of technical aspects like non-encrypted communication protocols and connectivity to OT networks being breached due to IT-OT convergence. But it is also true in terms of human factors. Cybersecurity doesn't begin or end with purely technical solutions. Investments must be made in employee training, creating realistic and enforceable security policies, and embedding processes to avoid security breaches. We mentioned earlier that something as seemingly insignificant as a small configuration change, whether due to error or malicious behavior, can cause major financial losses. That's the best case scenario. In a worst case production environment scenario, such changes also have potential to put employees at risk of serious injury or death. Given all the factors we've discussed so far, it's easy to absorb the fact not only that securing OT environments is a particular challenge, but that not doing so may introduce unacceptably high risk to the lives of employees and company assets. With all this in mind, tools used to ensure the security of OT environments must be designed and implemented with a particular perspective on how those environments should be protected. IT-OT convergence introduces security risks to process control networks due to factors like unsecured connectivity between IT and OT and complicated unsecured processes, all of which may lead to spillover attacks. But it also introduces the challenge of bridging the IT-OT security gap. Mutual frustration between the two worlds begins with OT engineers being forced to speak the IT language and IT employees being forced to accommodate OT requirements. Obviously, this gap is not easily bridged, and that is why any tool used to secure OT environments should also assist in bridging the IT and OT worlds. Taking everything we've just talked about into consideration, IT native tools and existing infrastructure are not a realistic security solution for OT environments. Only a platform that is purpose-built to handle the differences inherent in OT environments is suitable, and a single platform capable of integrating into your existing toolkit is ideal. Claroty solutions are able to distinguish between two alert categories. Each category includes numerous alert types. The first are process integrity alerts. Alerts like these are triggered when CTD is in operational mode and reflect critical changes to a production level process. 3 examples may include configuration downloads, new hardware assets being added to the network, or policy violations. Process integrity alerts typically happen due to network failures like human error, malicious attacks, and so on. They are countered by ensuring a level of visibility into the system that allows identification of changes to existing processes, thereby ensuring that zero-day attacks are identified and stopped immediately. This is the reason why in-depth visibility is one of the most valuable features of CTD, as well as being the core differentiator that gives Claroty its edge over other solutions. The second category of alert is the security alert. This refers to cyber attacks that take place according to characteristics already known and defined. These alerts are immediate indications of security breaches and must be addressed as soon as possible. CTD generates threat alerts based on anomalies, rules, signatures, and behaviors using proprietary algorithms. The first algorithm is the Behavior Anomalies Detector. This generates alerts according to baseline deviations. Baselines are behavioral norms generated from CTD's observations of the protocols and communications used in the system. Therefore, a baseline deviation is simply behavior that doesn't match the collection of traffic patterns that CTD has previously learned. In practice, this translates into information and alerts that focus on aspects like network changes, zero-day exploits, deviations from communication policy rules, and so on. The second algorithm is the signature-based detector. This works according to YARA rules and other rule-based approaches such as network traffic rules, in which deviation from a defined rule triggers an alert. CTD's threat database also includes signatures provided by the Claroty research team, with intent to alert users to zero-day vulnerabilities under our formal disclosure network traffic rules. Users can also create their own rules and can manually disable any threat signatures. The third algorithm is the Security Behavior Pattern Detector. This works by detecting non-security attacks such as man-in-the-middle and network scans. It also alerts on IT pattern security behaviors such as tag and address scans. The fourth algorithm is the Operational Behavioral Pattern Detector. This focuses on sensitive OT-related activities such as configuration file downloads and uploads, controller mode changes, key state changes, and firmware upgrades. In addition to flagging privileged commands to controllers, this algorithm combats OT-targeted attacks and sophisticated payloads. It flags OT operations that occur within the network over any communication protocol, allowing operators to make informed decisions and take actionable steps based on their organization's management of change process. The fifth algorithm is the rule-based threat detector. This generates alerts based on custom criteria that operators create to target specific events. For example, an operator could create a rule that flags out-of-range values or communications that are considered suspicious. Now we're going to enter the CTD demo system and see what the theory we've just learned actually looks like in practice. We are now in the CTD user interface. This is the default dashboard view. Before we focus on the threat detection section, we need to familiarize ourselves with the two different modes in which CTD can operate. Clicking the gear wheel icon takes us to the Configuration Settings menu. Under Management, we'll click the General tab. Here, we see the two different modes in which CTD can operate. These modes are Training Mode and Operational Mode. In Training Mode, CTD builds initial baselines and policies by using deep packet inspection to detect and store the network activity of all assets that are part of the site. Training Mode is a listening and learning mode. In this mode, the system does not generate process integrity alerts. So if any configuration downloads, policy violations, new asset additions, or asset configuration changes take place, relevant alerts will not be generated. The reason is that in training mode, CTD is busy building behavioral baselines, that is, learning what is and is not acceptable behavior within your network. The Alerts page is part of the Threat Detection section. The first thing we see is the numbers of process integrity alerts and security event alerts that have been logged by the system. This page has filters that allow you to search alerts by type, status, category, and free text. It also has view selectors that allow you to see alerts as rows of listings and as a layered topology view or network topology view that highlight the asset the alert originated from. When we get to the demo, you may notice that compared to earlier versions of CTD, the search and filter components in version 4.7.1 have been rearranged and renamed to improve the overall user experience. You will also see a line-by-line listing of individual alerts, with an option to group similar alerts into stories. There is an option selector that allows you to add additional columns for different information categories. There is an alert toolbar that allows you to create widgets and reports, show assets, events, virtual zones, and zone rules that are related to any listed alerts, to approve or archive alerts, and assign alerts to other users for processing if you need to. To optimize CTD database performance, CTD version 4.7.1 brought some changes to the length of time for which inactive alerts are retained in the system. In general, alerts that are inactive, in other words, that are not repeated, are deleted after 12 months. Also, all host scan, port scan, and login alerts are deleted after 3 months. Once CTD is switched to operational mode, alerts based on behavioral deviations will start being generated. However, it's important to remember that these alerts are generated based on traffic being identified and compared to the stored baselines and policies. CTD generates alerts on identified threat activity early in the kill chain. Even though it doesn't generate process integrity alerts in training mode, CTD is still able to generate security-related alerts. So, if CTD detects a threat signature within your system, it will be alerted on, regardless of mode. Now that we know the difference between training and operational modes, let's start with the threat detection overview. CTD is designed to give early identification of threats by relying on its in-depth knowledge of protocols, configuration, and communication flows. The system identifies known threat attacks, zero-day attacks, and attacks involving sophisticated OT payloads early on in the kill chain. While CTD is active, it continuously monitors the network traffic for threats and policy violations, providing the user with the visibility needed for quick response to unacceptable events within the OT environment. Here, we can see that we have a very high number of events, but a much smaller number of open alerts and open stories. We'll get to the actual definitions in a moment, but what these numbers mean is that the SOC engineer does not have to deal with every single event that CTD actually detects within the environment. Remember that event is a generic term, referring to a network-related event that may or may not have suspicious motives. On the other hand, alert refers to network-related events that the system knows or strongly suspects are suspicious. As such, you will only receive notifications of events that are considered suspicious. All events, whether or not they imply a threat to your OT environment, are transparent to the system, and you can review them at any time. Many generic events may simply be false positives. As in all sections we've dealt with previously, this dashboard is completely customizable. You can edit the dashboard and add your own widgets and data to be monitored. And, as before, it's also interactive, so if I click on any section within the overview, I will be transferred to the relevant page with that information available to view. A story is simply a set of alerts that CTD correlates after determining that the events are related. If I click this configuration download alert, I will be transferred to the alert view. This is a detailed description of the relevant alert. The view starts with the name of the alert, a description of what actually happened to cause the alert, and a section that explains what the alert means. Now, this is important both for non-OT native and non-IT native personnel who don't really understand the reasons why a configuration download took place, or why a threat signature has suddenly appeared within your environment, as the alert view page for each alert bridges the first knowledge gap between IT and OT by providing contextual detail for every event that has happened within your system. At the top of the screen are some buttons. Calculate score refers to the alert score. CTD calculates the score automatically, but we can always recalculate if needed. Or, if the feature is turned off, we can calculate the score manually. CTD is capable of saving network data packet capture files. These files are called PCAPs. This is generally done if you need to know in depth what happened during specific events. Whenever relevant PCAP files are generated by CTD, it is possible to download these files, then analyze them using a packet analyzing tool of your choice. By default, CTD always records and stores PCAP files for known threat alerts. If you need CTD to automatically generate PCAPs for less serious events and alerts, you must enable this capability using the Settings menu within CTD. Automatic PCAP recording capability can be enabled for separate networks that are part of the site that is being protected. If PCAP recording capability is enabled for a particular network, PCAPs can be recorded using either or both of two methods. PCAP collection can focus exclusively on detecting and recording data relating to known threats, on detecting and recording all incoming data related to the specific network, or both. If needed, PCAPs can also be recorded manually whenever needed, and the recorded PCAP allocated to any particular network. If PCAP recording capability is enabled for a network, PCAPs can be recorded using Berkeley packet filters or BPFs. In this way, PCAP collection can be focused exclusively on detecting and recording all data or specific incoming data related to the specific networks. If you want to record PCAPs manually, read the instructions on how to do so in the most current version of the CTD administration guide. As well as handling alerts themselves, users also have the option of assigning alerts to other CTD users. Having been notified of and having investigated an alert, we can approve or archive it. Alerts must only be approved after being thoroughly investigated and determined to be the product of a valid, non-threat event that should be allowed to happen. Alerts are archived when the relevant event was investigated and determined to be the result of unacceptable behavior within your network. The procedure for handling alerts differs depending on the alert type. For example, if we approve a policy violation alert, the alert is added to the policy database. But the next time the same type of policy violation is logged, no alert will be issued. If the policy violation alert is archived, then this event type will generate an alert whenever another event of the same type is detected. Another example is a new asset alert. If a new asset is approved for your environment, that asset will be added to the CTD database. Like the policy violation alert described earlier, if another asset of the same type is logged, it will not be alerted on. If the asset is archived, CTD will generate another alert if a new asset of the same type is logged. Another typical example is configuration downloads. If we approve a configuration download alert, CTD will still generate alerts for configuration downloads of the same type, because this is high-risk behavior. However, if the same type of configuration download happens again between the same two devices and is approved, the approval will influence the alert score. So, with each alert approval, the alert score will be lower. CTD's alert scoring is simply a method of managing and controlling alerts. A number of different calculation factors are used to enforce the alert scoring rules, and if the detection algorithm decides that an event warrants investigation, each individual alert receives a score ranging from 1 to 100. Admins can adjust the sensitivity value to suit their own environment. The alert scoring system is a detailed and transparent method of assessing the level of risk inherent in each alert, and this allows CTD to constantly improve its ability to distinguish severe alerts from mere notifications. The Show Indicators section presents us with a table in which we can see all the factors that have contributed to the total alert score. For example, the configuration file download is classed as an OT operation that was previously approved in the system, but never between these particular zones or assets. Essentially, what this means is that the two assets are using an unapproved communication pattern for the first time. In OT terms, that represents a substantial risk, and this factor actually contributed more risk points to the total score than any other indicator. An event like this would definitely be a red flag to any SOC engineer. Just above the indicator list are the three most significant indicators contributing to the alert score. We can also see the total score points. Now, although the total score for this alert is greater than 100, it is capped at 100, as any score above this percentage is academic in terms of severity. The root cause analysis is basically a brief story that tells us what led to the alert. The story is laid out as a timeline consisting of a series of interlocking steps. It allows a user to quickly grasp the alert as a sequence of events, rather than as a simplistic statement of what happened. To a network engineer, this is helpful in terms of deciding whether a specific event is malicious or not. For example, this analysis tells us that there was a host scan. Deciding whether a host scan is malicious or not depends on the security posture of your site. It may or may not be acceptable, and it should always be investigated, but by itself, it doesn't necessarily indicate an attack. However, what we see next in the timeline is an active remote session from an external asset to an engineering workstation using the RDP protocol. Together, these two events are now starting to look like an attack pattern. The events that follow involve two configuration downloads. The complete analysis paints a picture of what is likely a cyber attack. Now, by comparison of what we've just seen, imagine each one of these events having to be investigated separately. The relevant SOC engineer's job immediately becomes a great deal more difficult because a number of different events somehow need to be pieced together in context within a quick enough span of time that still allows meaningful action to be taken. With CTD, the entire sequence is automated. Following from the root cause analysis, which allows us to quickly grasp what happened, we move to the mitigation steps, which tell us what active measures and countermeasures to take in relation to the alert, and the alert section, which gives brief summaries of the source and destination assets involved in the event. If we click the Event Details button, we're presented with a more detailed version of the earlier root cause analysis. This readout contains a level of detail that needs a bit more technical knowledge to investigate effectively. Now, we've seen that this event involved configuration changes to hardware. So at this point, the most important thing we can know is what configuration steps were actually made. To find out, let's click the Show Diff link. In this window, the red text represents code that was removed from the standard configuration. The green text represents code that was added. Providing details like this to an OT engineer will allow the engineer to decide whether configuration changes are valid or invalid. Now let's look at the Events section. This section shows a dynamic table of all networking events that have been logged within CTD. Remember too what was mentioned earlier. This table shows events regardless of whether or not they are considered alerts that might impose risk. This lets you review the operational life cycle of your site, because every change that happens is visible. Next, let's look at the Rules section. The Zone Rules mechanism provides a way to fine-tune the system communication rules with very high accuracy, using a simple interface that is similar to a firewall management interface. Something else to remember is that in version 4.7.1 of CTD, a minor change was made. If zone rules are downloaded as CSV files from an EMC, each downloaded zone rule contains the name of the relevant site. When CTD is switched to operational mode, zone rules are applied to the network traffic. At this point, you can manage the rule list and customize it as needed. You can review, delete, validate, or modify Claroty provided zone rules, or create new rules based on specific needs within your environment. Zone rules are applied to virtual zones, as we learned in the earlier visibility module. As can be seen here, these are firewall-like rules that either allow traffic through or trigger an alert. According to, for example, defined behavior between a source zone and destination zone, on a specific protocol, on a port category or access type, and so on. Users can also add their own rules. Now, those of you who are familiar with network segmentation processes will know that it's usually a long, tedious task in which many parameters have to be taken into consideration to finalize the segmentation. If you have CTD, most of the tasks involved are done automatically, and alerts are generated if segmentation rules are violated. So now we have virtual segmentation. However, if you go a step further by integrating with the Claroty firewall integrator, you can also integrate the policy rules into the firewall. This means we have progressed from virtual network segmentation to physical network segmentation, because the firewall will now stop communications according to the policy rules you've created here. This would be the source. In this instance, a typical source might be surveillance cameras. A typical destination might be HMIs. It's fairly common sense in networking to assume that a camera shouldn't be communicating with an HMI. Next, we specify whether or not this rule should be active on creation. Since this rule involves a prohibited event, the action should be alert, and communication will not be allowed. If you want to specify exact parameters according to which this rule will take effect, the parameters are specified using these fields. In which case, all protocols, categories, and access types are valid, because cameras should never communicate with HMIs under any circumstances. Next, we add the rule. So now we have a rule that alerts on communication. What we've actually done here is create a virtual segmentation of the network. By virtual, we mean communication will not be dropped. It will only be alerted on. A baseline rule is an alert that is created based on anticipated changes to your environment or activities within behavioral baselines. As an example, you may want an alert when the baseline TCP from any port to port 5000 appears. To create this rule, you need to select a specific baseline. The available filter types are inactive for, and upon appearance. In this case, we will choose inactive for. Creating these rules requires a fairly deep knowledge of how traffic traverses within your environment. But for our purposes, let's imagine a single traffic stream occurring between two assets, carrying data regarding the rotational speed of an electric motor, and that if that baseline is not being detected every 10 minutes, then this motor is at risk of malfunctioning and causing harm to nearby personnel. So let's specify that if this baseline is inactive for 10 minutes, an alert will be raised. Or if we want, we can make it upon appearance, so that whenever this type of communication occurs within the environment, it will raise an alert. Next, let's have a look at the database of threat signatures and Yara rules. If we need to, we can disable any of the network signature rules. As a typical example, you may find that in rare cases, a signature turns out to be a cause of false positives within your environment. The listed Yara rules work in exactly the same way, with simple activation and deactivation. If I enter Claroty, internal Claroty rules will also be filtered for viewing and selection. Finally, let's have a look at the automatic alert resolution functionality. If there's a portion of my site for which a maintenance window is approaching, and new assets are to be added or configuration settings changed for two assets, and those behaviors are authorized, we know that regardless of being authorized, that behavior may still trigger policy violation and configuration download alerts. We don't want to have to deal with such alerts, as we want them approved automatically. Under Select Type, let's select Asset. Then under Select Filter, let's specify an IP range. Next, we specify assets within an IP range of 10.0.0.1 to 10.0.0.2. We select Approve because we know that those two assets will both generate alerts. We can also add more rules in tandem. For example, if the alert type is policy violation, then the alerts are approved automatically. We finish by naming the rule and saving it. With that, we conclude the section on threat detection, and thank you for your time. We've come to the end of our presentation. Thank you for your time.